Hello, this is my lab report on a falling Slinky. The purpose of this lab is to examine the motion of a stretched Slinky dropped from static equilibrium. Some of the fundamental physical principles include Newton's first and second law. Newton's first law states that an object that is in motion or at rest will remain that way unless there's an unbalanced force that acts upon it. And Newton's second law gives us the equation F net is equal to the change in momentum over the change in time. I've also included the position and velocity update formulas. Gravity is a constant force that is always pointing down towards the ground. The force of gravity, also known as the weight force, is the force between any two objects with mass. For a falling object, this is calculated by multiplying the gravitational constant g and the object's mass. Drag force is the resistance force that is opposite to the direction of motion. In the example of the experiment, the drag force is acting against the downward motion of the bottom end of the Slinky. Knowing the force of gravity and the drag force, the two values can be added to find the net force. There will be two different models in this experiment, one experimental and one computational. The experimental shows the observed position versus time, and the computational shows the predicted position versus time. In our results, the bottom of the Slinky remains at rest with tension and gravity being equal and opposite forces until the top end of the Slinky falls and meets the bottom end, causing it to fall as well. In the video, you can see the top end of the Slinky being let go while the bottom end remains at rest until it's hit by the top end, causing both ends to fall together. The system is the Slinky and the surroundings is the Earth. The origin of the coordinate plane is said to be at the bottom of the Slinky. In our initial conditions, the mass of the Slinky is said to be 0.204 kilograms, and the initial position of the bottom end of the Slinky is edited to match the position of the bottom seen in tracker. The initial velocity of the bottom end remains to be 0 since it's starting at rest. As for the proportionality constant for the magnitude of the drag force, the constant b is determined later on by guessing and checking what value best matches with the experimental model. In our first calculation loop, we're predicting the motion of the bottom end of the Slinky before the top end has touched it. This is when the total forces acting upon the bottom end of the Slinky are the tension force and the force of gravity. In our code, we've implemented the formulas for the force of gravity and the tension force and summed them up to find the net force. During this time period, it's expected that our object remains at the same position at rest due to the tension and gravity being equal but opposite forces. In our second calculation loop, we're predicting the motion of the bottom end of the Slinky after the top end meets it. This is when the total forces acting upon this end of the Slinky are the force of gravity and the drag force. In our code, we've implemented the formulas for the force of gravity and the drag force and summed them up to find the net force. During this time, this is when the bottom end of the Slinky moves and falls to the ground. Here's the graph of both the observed position and the predicted position as a function of time. The computational model shares a similar shape to the experimental model with how the object remains at the same position in the first couple seconds and starts to move after the amount of time. However, even when we account for the drag force in the code, our predicted model is slightly off from what we observed. So why does the bottom end of the Slinky stay stationary? Well, according to Newton's first law, if an object is at rest, it will remain that way unless an unbalanced force acts upon it. In this case, treating the top and bottom end of the Slinky as two separate objects, the bottom end stayed at rest due to the force of gravity and the force of tension. These forces were equal in magnitude but were opposite in direction, making the net force equal to 0. It's only when the top end comes into contact with the bottom end that the bottom end starts to move. That's the unbalanced force that causes the bottom end to go into motion. What if there was an object attached to the bottom of the Slinky? Would it still remain stationary? Yes, it would follow the same path of motion as if there were no object attached. Having an object attached to the bottom doesn't change the basic principles of Newton's first law that allow the bottom end to remain stationary. So, possible sources of error could have come from mistyping my code, setting the wrong initial conditions, or inaccuracies made in Tracker when plotting the points of mass. In Tracker, it was difficult to maintain the same point on the object with the low resolution of the video. This affected my ability to track the same point at the bottom of the Slinky. All of these are possible contributing factors to the discrepancy seen in my position graph. So, what can we conclude from this experiment? While the computational model generally follows the same path of motion as what was observed, there can still be discrepancies when comparing it to the real-world example, even when accounting for drag.